All right, so questions. So I'll tell you what I told the last section. I can interpret silence a few different ways. One is that that you have no questions because you've already made a tree by hand in memory, and you've got at least one form of traversal working, and you've got your add function working, and things are making sense, and so you have no questions. That's a good place to be. The other possibility is that you have not done those things, and you don't have questions because you haven't gotten to the point yet where you're bumping into issues. And that's a problem if that's the case, okay? Because I want to move on. I want to start talking about deletion today. And from this point forward, we're just going to be working with these data structures more and more. And if you haven't actually coded anything yet as far as, you know, this arrow left, this arrow right, and so on, then these lectures are going to make less and less sense going forward. Which means that when you do get to the point where you're ready to delete, you're going to have to relearn it all, either rewatch the videos or something, right? So I really hope that people are keeping up with this work, okay? It's Wednesday. You have, counting today, 9 days left for this assignment, okay? And you can ask questions even if you don't understand everything about what it is you're asking. Right, if you're trying to make a tree by hand in memory and you're not sure how to do that and you're just getting seg faults or something, right, that's good stuff to talk about.
Can we go for L&R traversal for like a full tree?
Absolutely.
Pseudocode.
So you said pseudocode or just going over the traversal? Yeah, let's make a tree. All right, in which order?
L&R.
LNR. Okay, left node right. It's a recursive definition. This means first we want to traverse the left subtree, then we want to print out the root, then we want to traverse the right subtree. Okay. So there's a subtask which is traversing the left subtree in left node right order. So it means first traverse the left subtree. Well, if we work through it, that's just going to print out the root data, which is 5. Then print out the root of this tree we're traversing, which is 10. Then traverse the right subtree, since it only has a root that's going to give you a 15. Okay, that's the end of traversing this tree. That's the end of traversing the left subtree of our start. That's step 1. Step 2, print the root data. That's our 20. And then step 3, do an L&R traversal on that. So here's our recursive call to L&R, and the tree we're trying to traverse is the following. Okay, well, 2 steps. First, traverse null. That's not going to print out anything. Step 2, print the root data. That's a 30. And then step 3, do an L&R traversal on that. So that's a new subproblem. L&R traversal on this. Well, traverse the left subtree, which is null. That doesn't print anything. Print the root data. That's a 40. And then do an L&R traversal on that. Okay, new subproblem. Print the left node is 45. Print the root node is 50. Print the right node is null. We're done traversing this. We're done traversing this. We are done traversing this. We are done traversing this. We're done traversing the whole thing. Okay, very, very recursive. Let's do node left right. Okay, so first we're going to do the node, and then we're going to do the left subtree, and then we're going to do the right subtree. Yeah?
When you're calling just the node, is that just root?
do you mean when you're calling the node?
So, like, when you're trying to, so, like, step one.
Mm-hmm. So that's just a printf statement, just printf, in this case, root arrow data. So let's,
Step one?
for a node left right, so let's go ahead and do the pseudocode for that. So step 0, if the tree is null, return, nothing to do. Otherwise, in this case, since we're doing node left right, first thing we do, print the root node's data. Then do node left right on the left subtree, then do node left right on the right subtree. Alright, so if we do our original tree in node left right, step 1, print the root node's data, that's a 20. Step 2, do node left right on this tree, which is 10, 5, 15. So we're going to start a new memory frame here. Here's a 10, here's a 5, here's a 15. So you want to do this in node left right. Well, what does that mean? Print out the root node, that's a 10, and then traverse the left subtree, that's just going to be a 5, and then traverse the right subtree, that's a 15. Now we finished traversing that tree, which means we finished the left part. Right, so we did the node, we did the left part, now we have to traverse the right part in node left right order. Okay, how do we traverse this tree? First print out the root, then traverse the left subtree, which is null, nothing to do, then traverse the right subtree, so 40, 50, 45. How do we traverse that? Print out the root node, 40, traverse the left subtree, that's null, nothing to do, and then traverse this tree. How do we traverse this tree? Print out the root node, then print out the left subtree in NLR order, that's going to be 45, and then the right subtree is null, nothing to do. We're done with that, we're done with this tree, we're done with this tree, which means we're done with that 30, which means we're done with that subtree, which means we're done with the whole thing. That should be your NLR traversal. Say again? Yeah. And for a different order, that statement 1 goes somewhere else. If it's left node right, first do LNR on the left tree, then print the data, then do LNR on the right tree. If it's left right node, do left right node on the left right node on the right, and then print the data at the end. Yeah. It gets harder with fluffier trees. You want it fluffier? Oh boy. Like that? Okay. Which order do you want to do? Okay. This is why we have computers, so we don't have to do this ourselves. Left node right. Okay, first thing we're going to do is traverse this tree, and then we're going to print the root node, and then we're going to traverse this tree. So this is where you go to your friend and you say, hey, can you traverse a tree that's like this? Right? And whatever they give you, that's the result of traversing this. And then you print a 20, and then you go to your friend and say, can you traverse this? And whatever they give you, that's the result that you do for that. So if we know how to traverse this, we know how to traverse the bigger tree, right? So can we concentrate on traversing this for a moment? Okay, so let's just do that. So here's a 10, a 5, a 3, a 7, a 15, a 12, and a 16. Okay, and I'll switch colors. So to traverse this, first we need to traverse the left subtree, then we need to print the root data, then we need to traverse the right subtree. So you find another friend and you say, hey, can you traverse this? Well, LNR says first traverse the left subtree, then print the root, then traverse the right subtree. And you can find another friend, or you might just know if you want to traverse a tree that just has one node in it, you just print out that node. Okay, so we're going to print out a 3, and then the root node, and then the right subtree. Okay, that's the traversal of this thing. And a 3-node tree, we don't have to recurse on paper. We know that when we drew this, it's going to be left node right. Okay, so traversing this tree gives me 3, 5, 7. And then I'm going to visit the root node, so I'll print out a 10. And then I'll traverse this whole subtree in left node right, which is going to be 12, 15, 16. Okay, so this is the result of traversing that smaller tree that's all of this stuff. So this is basically step 1 of our first call. And then we print the root node. And then we need to traverse this tree same way as we just did. And it's going to be the same thing. First we'll traverse the left subtree, which will be 25, 30, 35. And then we'll print the root node. And then we'll do the right subtree, 50, 60, 70. And this will all be step 3. This was step 2. And if it was an even bigger, fluffier tree, right, this might have been the left child, we would have done all of this, and then we'd print the root node that was up here, and then we'd do the same thing on the right. So that gets increasingly complex the more complex your trees are. Increasingly complex for us, right? Always pretty straightforward for the computer, because the computer can remember where it was. We have to use different sheets of paper and so on. We'll do a worksheet later on this week where you'll get to do recursion on paper. Yeah?
Speaking of recursion, so the search function.
Mm-hmm.
I'm aware that it has a similar kind of recursion as LNI.
Mm-hmm.
That's what I would do. You have a, if null turns to 0, and then right after that, if you found the string, then return 1. And then after that, you just do what you do, you just pass to the left, go to the right,
Mm-hmm.
and then it's the other direction. But how, when it finds, so when it finds the string, the plate, in, say, the second or third iteration of the search function,
Mm-hmm.
how do you pass that it found the like the find, I guess you said, all the way back up to the original call function?
Yeah, it just kind of happens, which is sort of miraculous. So search, so here's our search function. We're searching for a number in a tree. If root is null, return 0. If the root data is equal to our number, return 1. If our number is smaller than the root data, then return search root left. comma number. Otherwise, do your recursive call on the right and return the result of that. Right, so it's that return value that's going to trickle up.
Yeah. We don't have that search function, or the next call search function in the return thing, then.
Right, right. So if I'm searching for 15, I'm going to say 15 smaller than my data. Let's search for 15 in this smaller tree and return whatever that returns. And my call to that's going to say, well, 15 is bigger than 10. Let's look for a 15 in this little tiny tree and return whatever that returns. And when I search for that, it's going to look at the root and say, hey, my root's equal to 15. I'm going to return a 1. And so my call to search this is going to return a 1, and my call to search this is going to return a 1. And if I'm copying the first and last name into those string pointers that I called first and last, right, those will trickle up as well. It's definitely a touch of magic. Yeah.
I have a question about clarifying some stuff on the instructions.
Mm-hmm.
For, like, for example, the add and delete function, well, if it's supposed to return the new in parentheses,
Mm-hmm.
the question mark code, I'm not really certain what that means. What's the
Okay, so this is a excellent point to think about. So suppose we just had an add function. You just pass it a root and you pass it a number to add, right? And suppose we're starting with an empty tree where root is null, okay? If my main program says root equals null and I just say add root comma number, root is not going to change, right? I might do some things in memory down here in my add function, but root is a local variable inside main. Anything I do inside add is not going to change the value of root. So my tree is always going to be null. So when we call this, we say something like root equals add root comma number. Okay, the only time that this matters is if our original tree is null. In that case, we're moving from a null tree to a tree containing one root, one node, okay? And in that case, the return function from this is going to be different from the root value that you passed in, because you passed in null, and now the root is, you know, whatever your first node is. But once we have a tree, you know, we've got a 20 and a 10 and a 15, and if you want to add a 25, right, it's going to start here, it's going to move to the right. Let's say this was 22. It's going to move here, it's going to move to the right, your 25 will go down here. Your root's never going to change, okay? So your add function only changes the root in one case, which is when your root is initially empty, it's null, and then it's going to become something not null. But we don't want to worry about when that case is, so we're always going to take the return value and set that equal to root. So that parentheses new question mark is saying that, you know, you always want to return the root of the tree. Once in a while, that's going to be different from the original root, okay, but generally not. Deletion, which we're going to talk about next, right, is another case where if you're deleting the root of a tree, the root's definitely going to change, right, and so delete's going to have to return the root of the new tree.
Sorry, you said set whatever add returns equals root.
Set root equal to whatever add returns. So in your main program, you start off with root equal to null, that's your empty tree. When you want to add something, you call add, pass it the root, what you want to add, and the return value goes back into root. So root's always pointing to the top of the tree, or null if the tree is empty. Cool. All right, let's delete from trees. So here's a tree. And we want to delete a node from it. Okay, there's a few things we need to make sure happens. We want to remove the node, say we want to delete the 16. The 16 has to disappear. Okay. We have to make sure that this is still a binary search tree. If we just delete this node, right, 15 and 17 become orphaned. They've lost their parent. There's no way to get to them if this node just like goes back into the memory pool. And we can't make them both children of 18 because 18 can only have one child on the left. And we can't move 17 to the right because then it's not a binary search tree. So we need to keep this thing as a full bona fide tree in which we can get to every node. And we need to maintain this property that everything to the left of a node is smaller, everything to the right is larger. Okay, these are the issues in deleting. And it turns out if we want to delete anything other than the root of the tree, it's really easy to do. We're just going to do it recursively. If I want to delete the 16, what am I going to do? I'm going to call my delete function and say, delete a 16 from this tree. And whatever the resulting tree looks like, I'm just going to have 20 point to that on the left. And as long as my delete function successfully deletes a 16 from this tree, that will work perfectly. Well, how am I going to delete 16 from this tree? I'm going to say 16 is bigger than 10. Go ahead and delete 16 from this tree. And whatever tree you end up with, make 10 point to that on the right. Okay, how do I delete 16 from this tree? I'm going to say, well, 16 is smaller than the root. Let's delete 16 from this little tree, and whatever we get back, let's have 18 point to that on the left. Well, now I'm trying to delete the root of a tree. So the only work we actually have to do is when we're deleting the root. If we're deleting anything that's not the root, we'll just recursively call the delete function on the left or right subtree. Okay, so we'll put that in code in a few minutes. But the trickiest part is deleting the root of a tree. And it kind of makes sense because it's got, children, and if we lose the root, we lose access to all the children. So this is sort of the trickiest. All right, so deleting the root of a tree. Okay, I'll give you a couple of base cases. Base case 1, if tree is null, do nothing. But that should never happen. The delete algorithm we're going to talk about assumes that the thing you're trying to delete is somewhere in the tree. Okay? So this should never happen because a null tree has nothing in it. We can't be deleting from it. So assume thing being deleted is in the tree. That's going to simplify some of our work. So let's just look at this tree and let's brainstorm. Suppose I want to remove the 20, but I still want this to be a nice connected tree, and I want everything on the left smaller than things at the root, smaller than things on the right. So I'm going to replace the 20 with some other node. I don't want to move a whole lot of stuff around. I want to do as little manipulation of memory as possible. So I want to replace the 20 with some other node that still makes this a binary search tree. So can you find a number that I could put in place of the 20 that would still make this thing look reasonable? $30. Say again? 19. There's no 19.
Oh, you replace it.
Yeah. So I could put the 30 up here, and then I have to figure out where to put the 25. Right? Because that's a child of 30. Well, if 30 goes up here, 30's already got 2 children. Well, I could put the 25 up here. No, I can't. Oh, put the 25 up here. Okay, so if I put the 25 up here, that's going to be a really good binary search tree, right? If I move the 25 up here, 25 happens to be the smallest thing in this subtree, which means everything else in this tree is going to be bigger than 25. So if I make 25 the root, I know that everything in the subtree is bigger than it. I'm preserving my BST. Since 25 is to the right of the original root, everything to the left of the original root is smaller than 20, smaller than 25. So I've still got a BST. So that's one possibility, is put the 25 in place of the root. You could also do the 18, and the same logic applies. Everything over here is going to be bigger than 18 because it's bigger than 20, which is bigger than 18. And 18 is the largest thing in the left subtree. So everything else over here is going to be smaller than 18, but there's still one issue, which is 18 already has something on the left. Our 16 is going to be orphaned. But we could make 16 an adopted child of 10. And in this case, that works. But we need to know if that always works. So these are the two basic approaches we can use, and we're only going to be allowed to use one of these approaches for PA4. Okay, so this is the part where you can have something that works correctly but still not get points for it. Okay, so here's the required rule. Replace the root with the largest node in the left subtree. Okay, we're going to replace the root with the largest node in the left subtree. So 18 goes up to the root. And if 18 has a left child, then 18's parent will adopt that child as its right child because it's losing its right child, which is becoming the root. So it's got an open slot over there. There's one exception to this. Okay, if there is no left subtree, this makes no sense. Because there's nothing in the left subtree, there's no largest node in the left subtree. So if there's nothing in the left subtree, you can't do this. So in this case, just set the root equal to the root's right child. Because if your tree looks like this, it's got stuff on the right of the root but nothing on the left, how do we delete the root? Just change the root to point to that 30. But you can only do that if there's nothing on the left. Does that description make sense? So pop quizzes. Right, delete the 20, what takes its place? 10, right, largest thing on the left. Delete the 20, what takes its place? 15. Delete the 20, what takes its place? 10, it's the largest thing on the left. Delete the 20, what takes its place? 15, right? This should turn into the following. Okay. You could delete the 20 simply by moving the root down to the 10. You don't get points for that. Okay? You got to follow this algorithm. If there's anything on the left, find the largest thing in the left, replace the root with that. Okay, the only time you get to move the root down is if you've got something like this. Right, nothing on the left at all. Just change your root to the root's right child. Yeah?
So
Say that again?
we were trying to delete 16 in this
Mm-hmm. So none of this applies until you get down to this tree. Okay, and 16 will get replaced with the largest thing on the left, which is a 15, so you'll just get a 15 right here. So you'll have a 15, 17, and that just replaces this thing inside the whole tree. So your final tree would look exactly like this, except there's a 15 right there. We still got to go through the recursive case more carefully. All right, so let's code this. And let me stick to the same tree. All right, I'm going to put on some labels. So this is going to be the root. This 18 is going to be the largest node in the left subtree. And I'm also going to mark the node right before that, the prior node. And let's write some code to perform this change, right, to move this 18 up to the root. So there's 3 or 4 things that need to happen to make that move. We don't want to just copy the data value. Okay, we want to actually pick up the node and move it around and change what it's pointing to and so on and so forth. So our goal is to move the 18 to the root and then have the 16 adopted by the 10. So throw out some code that would help make this happen. Assuming we've already got these struct node pointers called largest, prior, and root. We've already found those and have them pointing to the appropriate places. What sorts of statements will we write from here?
So the address of the largest would be the address of root. So largest root is
Maybe root equals largest.
oh,
Yeah. So that's going to be the new root. And that's probably the last thing we're going to do, right? And then we're going to return that as the root of the new tree. Okay, good. What else?
Prior right.
Cool. Prior right equals largest left. Okay, so that's going to take this and it's going to pick up largest as its new right child.
is that the for all trees?
More or less, except when it doesn't.
It's like, what if like 18% of the child?
Yeah, so we'll talk about edge cases next. And there are some. All right, what else has to happen? Because if I return largest as the root, right, I've lost all of this parts of the tree.
Largest right equals root right?
Good. Largest right equals root right. So we take this thing which should become the root and we have it pick up this whole subtree as its new right child. All right, what else?
Largest left equals, yeah.
Yeah, largest left equals root left. So we take this new root and we have it pick up everything that's in the left subtree of the original root as its new left child. And before we do that, we need to make sure that we've used largest left to set prior right. Because if we do that after we've changed this, things will go wonky. All right, so we set up the right child of the new root. We set up the prior node to adopt the new root's orphaned left child. And then we've set up our new root to point to the proper thing on the left. And then we set root to be the largest value. Before we do that, we should probably free the root. And if you want to make a mess, step 1, largest right equals root right. Well, that's causing this to pick up that. So that's step 1. Step 2, prior right equals largest left. That's putting in this link. Step 3, largest left equals root left. So that's changing this to point to there. And then we free the root. And then we set our new root equal to what was largest, and we return that. If you can follow the squiggles, this is a good tree. That's the root of the tree, the right subtree is all of that, the left subtree is all of this, and 10's right subchild is now 16, 15, 17. So if you redrew that, it would look exactly like what we wanted. Yeah. That's just the start of it. So there's edge cases, okay? But you know, to do this, you need to find the largest node in the left subtree. Well, how do you find the largest node in the left subtree? Start with the left subtree. Okay, so let's just make a picture of that left subtree, which looks like 10 and 5 and 18 and 16 and 15 and 17. There's our only tree in the whole universe, and we want to find the largest node in this tree. How do we do that?
Go right, you find node and do it again.
Yeah, go right until you can't go right anymore. That's going to be the largest node. Right, that's because it's a binary search tree. So go right, go right, go right. Well, it happens we stop right here. That's the largest. And the node right before that, that's the prior node.
Never mind.
Okay. So you got to do that prior current business from linked lists, right? As you're moving down to look for the rightmost node, you've got to remember the node that you were at before. That's going to be this node prior. Okay. If this was our tree that we were trying to find the largest node in, we start from the root, go to the right, go to the right. 40 is the biggest node. The prior node is 30. Okay. So that's not too bad in itself, but it's another algorithm you probably want to code. Give it the root of a tree, it gives you back the prior node and the largest node, right? Or maybe it just gives you back the prior node and you just know that you move to the right to get to the largest, up to you. This business of adopting the orphan child, right? 18 is the largest node in this left subtree. It's going to take on 2 new children, okay, the children of root. So its left child will be orphaned. That can be picked up by its prior node. What about its right child? What if there's a right child that becomes orphaned? Then 18 is not the biggest node, right? If 18 is the biggest, it has nothing to the right. So at most, it's going to orphan 1 child, and the prior node can pick that up on the right. So this will always work. Okay, but there's an edge case. Okay, we want to delete the root. We have to find the largest node from the left subtree. Well, the largest node is just 10. You started the root, and you can't move to the right at all. But in this case, there's no prior node, right? The first node that we started at, that was the largest. So if we're doing this prior current pair business, we don't even get started, right? So this is another edge case. Yeah?
Root arrow right equals null would be a way of showing the edge case handling.
Mm-hmm. Right. So trying to find the largest thing in this tree, if root arrow right is null, then we know that the root's the largest. We know that there's no prior node. Okay. In that case, we're going to use this to take the place of the root. We know there's nothing to the right of this, and whatever was to the left of this, we can just keep that to the left. So this is an easier case to deal with, right? So this is largest, so largest right. So let me say if largest right is null, largest right equals root right, and we're done. Right, we don't have to adjust largest left, because it's just going to stay at the left subtree. But you have to make sure your code doesn't segfault by, you know, having some random value in prior that you never got to set because you didn't go through your while loop at all. Because if you while, largest right is not null, right? So it's a case to think about. Yeah.
Is these supposed to be a worksheet?
Yeah, I think tomorrow or Friday, probably tomorrow, I'm going to pass out a worksheet that we'll work on in class.
Okay, we'll do this mention.
We'll definitely do insertion. I don't know if we'll do deletion. We could try to do deletion. So the code is not critical, right? The code is not the takeaway message. The takeaway message is the algorithm, right? Find the largest thing, move it to the root, have it point to the left and right children of the root, and whatever it has on the left, have the prior node adopt that. Unless there is no prior node, in which case you simply move this up to the root, pick up the right subtree on the right, leave the left subtree as it is. You want to make peace with the algorithm, right? Work it out with some sample trees, draw some pictures, and then write the code from that, okay? If you write this down in your notes and you go home and you start trying to figure out how to code your algorithm based on this, you're going down a really bad path, right? It's going to be really confusing because trying to glean the algorithm out of this is hard, right? Try to understand the algorithm, and then you should be able to write code that will do what this code is doing, right? But you might not call this largest and prior. You might call it greatest and, you know, node before greatest or whatever, right? Do something that makes sense for you, and write the code from there. And then play computer, right? Make your tree and go through your pseudocode and forget about what you know about deleting from a tree. Just do what your code says. Follow it blindly, step by step, and then when you're done, step back and say, how does my tree look? And if it's, you know, got flames coming out of the top or something, then something went wrong in the algorithm. And there's a lot that can go wrong in here, right? It's really easy to abandon nodes and have them just kind of dangling out there and no way to get to them. It's really easy to accidentally make a cycle where you have, you know, a right child down here that points back up to the root if you do these in the wrong order. And then you do your LNR traversal and it just prints out forever because it keeps following, but when it gets down here, it goes back up to the top or something, right? But discover those things on paper or on a whiteboard, okay? Start with simpler trees and go through your pseudocode, see what it does, and then build up from there. Okay, let's do the recursive case. We got 5 minutes. So a general delete function, delete a number from a tree with the given root. If the root of the tree is equal to the thing you're trying to delete, do all the stuff we've been talking about for the past 25 minutes. Okay? That's all we've been talking about is the case where we're deleting the root. So if it's the root of the tree you're trying to delete, right, the root data is equal to the number, do all that stuff. Otherwise, we need to recurse. And the recursion is fun to write. So if the number we want to delete is less than the root data, call your delete function on the left subtree, because since it's smaller than the root, the data has to be in the left. So delete it from the left subtree, and then change the root's left subtree to be whatever the resulting tree is. Else, yeah, it's just like search, it's just like add. And then return the root. I should never have a case where root is null if I started off by making sure the thing I'm deleting is inside my tree. If I don't know if the thing I'm deleting is inside my tree, it's possible that, you know, my number is smaller than the root, but there's nothing to the left, and so I might end up trying to delete from a null tree. So I would want to check up here which says if the root is null, don't do anything. But if you guarantee that you're always deleting something that's in your tree, then one of these cases will eventually fire. So this is a case where we generally recurse to a subcase, but if we're not able to recurse and we have to actually do the work ourselves, the work is very, very large, right? It's not just add one to the previous answer. It's actually, you know, do this big long algorithm with all these edge cases and danger and scary things. So that's a little unusual from other recursions we've talked about.
Was calling our search function before deleting kind of like overkill? If you're going to try to search instead of just like assuming it's there?
So it depends on the application, right? So in your main program, I might say delete a plate that doesn't exist. So you want to deal with it somewhere. Inside here, right, I could say if root is null, then what am I going to return, right? I could just return the original root. But if I want to know that my delete didn't actually delete anything, I don't necessarily know that just from getting back the original root. So it depends, right? And I haven't specified, so I don't really care which way you do it. Just make sure somewhere between your main program and this, if I try to delete something that's not there, I get a message saying plate's not there. All right, so think about this, start coding some stuff up, start writing some pseudocode, playing computer, whatever approach you like, and bring questions tomorrow, okay? And I think Friday I'm going to do as a lab day. I've got to decide, but I'll post something later on. I think we're going to make Friday an open lab, which means no new material, but if you want to work on code, you can come in and we can work on code and answer questions and stuff like that. So you really want to try to get some progress before Friday if you want to take advantage of that. But I'll post an announcement later on today and let you know if that's happening. All right, I will see you next time.